I'm going to start chapter 23 now. That's all about electric potential energy and electric potential. To cover this topic, we're going to build on things learned in Physics 1050 or 1020, and that's all about work and energy. So I'll do a very quick recap here, but if you're a little fuzzy on those issues, you might want to go back and recap chapters 6 and 7. We know kinetic energy is given by 1/2 times m times v squared. If we have more than one object, to get the total kinetic energy, we add up the kinetic energy of every object. So total kinetic energy is the sum of every individual kinetic energy of every individual object. So that's the sum of 1/2 times each mass times its velocity squared. Okay, next. Potential energy can be thought of as an energy of interaction. If you have a mass held up in the air, it interacts with the earth, and there's a potential energy due to gravity. What we know about a change in potential energy is that a change in potential energy delta U is minus the work done by the force. If all of the forces in a system are conservative, that means we don't have any forces like friction, then we see a couple of things. First of all, for every one of those conservative forces, we can associate a potential energy function. And that potential energy function is related to the conservative force by F equals the change in potential energy over distance. So what I have here is that the component of force is minus the derivative of the potential energy with respect to that dimension. So the x component would be minus du dx, the y component would be minus du dy, and so on. If you were a graphical kind of person, you might think of the fact that the force is minus the slope of a potential energy graph. Then the second thing is that the total mechanical energy in a system with only conservative forces, that total mechanical energy is conserved. Remember, mechanical energy is the sum of kinetic plus potential. So in general, we write conservation of energy. I'm just going to make myself a little bit more room, is E final equals E initial plus work done by non-conservative forces. If we don't have any non-conservative forces, of course, they can't do any work, and E final equals E initial. E final is kinetic final plus potential final. That's equal to E initial, which is initial kinetic plus initial potential. Another way to write this same expression would be to say that delta E, the change in mechanical energy, is the change in kinetic plus the change in potential, and that has to equal 0 if there are no non-conservative forces. Energy can switch back and forth between kinetic and potential, but we can't gain energy and we can't lose energy. Last concept is work. Work done by a force. The general definition is that work is the integral of force over distance. The scalar product between force and distance. So that means you could write it as F times dr times the cosine of the angle between them. That's for a variable force. If we had a constant force, we would say then that the work is F dot delta r, or F times delta r times the cosine of the angle between them. Okay, we're going to use all of these ideas. We're going to apply it to electric force and electric fields. That's going to lead us to talk about electric potential energy, and from there we're going to talk about electric potential. We're going to be discussing electric potential energy, but first let's recap gravitational potential energy. Then we can use our ideas of gravitational potential energy as an analogy to develop electric potential energy. So let's start. If we have a mass m above the surface of the Earth, it's going to feel a gravitational force. And that gravitational force is what we call weight, and that force is equal to m times g, which is the mass times the field. Okay, let's label our diagram a bit. So there's our mass m. It feels a gravitational force, Fg, which is the mass times the field. Remember, G is the agent of the force. And G has a magnitude of 9.81 meters per second squared. Of course, that's on Earth, and it's towards the center of the Earth. G is the gravitational field. Let's put that in our picture. That points straight down towards the center of the Earth. Okay, so if our object moves in the field, then the force due to gravity, or the weight, is going to do work on the object. So let's say that our object moves from point A down to point B. Point A to point B. In this case, the force is parallel to the displacement and the work done is positive. So force parallel displacement, work is positive. Our object, of course, doesn't have to go down. It could also move up. So let's say we have our mass over here and it moves upwards in the air from point A to point B. If you were thinking about what could be physically happening here, let's say in our first picture, we hold an apple up in the air and we just let it go. It'll fall down. That's when our force points down and our displacement is down. Over here in our second picture, let's say the apple is in our hand and we throw it up in the air. Then it moves upwards from point A to point B. In our second picture, the force hasn't changed. The force due to gravity still points down. It's still m times g. And our gravitational field hasn't changed because that's made by the Earth. Our apple can't affect it. But in this case, the work done would be negative. So if force is anti-parallel or in opposite directions, this is where our work done is negative. Okay, why don't we write down an expression for our work next? The work done on our apple or on our object as it moves from A to B is the integral over the path from A to B of the force over that displacement over the path it travels. So that would be the integral from A to B, F times dl times the cosine of the angle between the force and the displacement vectors. Okay, so we've covered positive and negative work. We've covered the definition. Now, it turns out that our work done is actually independent of path. What that means is if our object in our first picture doesn't go straight down, let's say it takes some sort of curvy course and goes down that way in our first picture, or if in our second picture it also does a curvy path back and forth until it gets up to point B. In either case, the work done by the force due to gravity would be identical. That tells us that the force due to gravity is conservative and we can associate a potential energy with that force. Okay, let's bring that part in. So the work done as our apple or our mass moves from point A to point B is minus delta U. That's a relationship between work and potential energy. That's minus or negative of our final potential energy, subtract our initial potential energy. And we also know that the change in potential energy is m times g times the change in position. So that gives us minus m times g times delta y. And the definition of our potential energy function is U equals m times g times y. So here in this equation, y is the distance above the ground. No matter what physics problem you do, you always need a coordinate system. So in our coordinate systems, we would normally take the ground as y equals 0. Positive y would be upwards. Okay, and that's true on both pictures. Y equals 0, positive y is upwards. Okay, so last couple of things to mention. If we're looking at our first picture and the path is in the same direction as the force or the field, so that's this picture. So the force is down, the field is down, and the path ultimately is down, even if it does wiggle a bit on the way down. What happens in this case, and this is important enough to write down, is that the work is positive the potential energy decreases, U decreases, or in other words, delta U is negative because it gets smaller. When our potential energy decreases, our kinetic energy increases. So delta K would be positive, and our object will speed up. Let's see, what other note would we say here? If we have an object M and we release it from rest, it would fall to the ground where our potential energy would be 0. So if U is M times G times Y, our potential energy would be 0 at ground level. Okay, so that's what happens when the force and field are in and the displacement are all in the same direction. What about our second case when the object moves up while the force is down? So what if the force and the displacement are anti-parallel? Even if it wiggles a bit on the way up, the net displacement is still up. So in this case, we have that the work is negative and our potential energy increases, which means that delta U is positive. If our potential energy increases, our kinetic energy decreases, which means delta K is negative, and our object slows down. And this is certainly familiar from everyday life. As something goes up into the air, gravity points downwards, the acceleration is downwards, so it slows down. Okay, I think that was a fairly thorough recap of gravitational potential energy, but again, if you want to review, you might want to check out those earlier chapters. So now I think we're ready to start talking about electric force and field and potential energy. Let's start by talking about a positive charge, Q, moving in an electric field. Since I'm stressing positive charge, I'm going to invite you to wonder in the back of your mind, what about negative charges? We're going to get there, but you might start to lay the groundwork in your thoughts for it. If we have a positive charge Q and it's in an electric field, it's going to feel an electric force because of that field. And our electric force, Fe, is equal to the charge times the electric field. So remember here, our electric field is the agent of the force. Now, electric field is a little different than gravitational field. Our gravitational field is always towards the center of our massive body. Our electric field is outward from a positive charge and inward toward a negative charge. So for direction, I'm just going to say that electric field is from positive to negative of the source charges or the charges creating the field. In my pictures here, I'm trying to keep a close analogy with gravity. So I've got a capacitor where the top plate is positive and the bottom plate is negative. That means that the electric field points down everywhere. So the electric field is straight down, looks like our gravitational field. And here I have my charge Q. So let's label that Q, and I'm even going to put a plus on it to remind ourselves that we're talking about positive charge. So the force on our positive charge here is going to be the electric force. Let's draw in that electric force. Fe equals Q times E. So if our positive charge moves in the field, then the electric force is going to do work on the charged particle. So work done on the charge by the electric force as our charged particle moves from point A to point B. So let's say we start at point A and we go down to point B. The work done as the charge goes from A to B is equal to the integral from A to B of the electric force dotted with the path. So that's the integral from A to B of F times cosine theta times dl, the electric force. Okay, so I've put in my points A and B. In my first picture, my electric field is down and my charge is moving from up to down, so our charge is moving down. In this case, our work is going to be positive. So force and displacement parallel, work is positive. Okay, now just like we could throw an apple up in the air, we could throw a charge up in the air. We could project this positive charge upwards. You can't exactly throw a charge with your hand, but you can make it move upwards. So your charge doesn't necessarily have to go in the same direction as the field. It can move opposite the field. So let's say it moves from point A to point B this way. So if your force is opposite your displacement, then your work is negative, same as gravitational work. Okay, and while we're here, why don't we just make sure we label our electric force. So the electric force is the charge times the field. If our charge is positive, then the force is in the same direction as the field. It turns out that the work done by an electric force is independent of path, just like the work done by gravity. So we could take our squiggly line to get to point B. So whichever way we go, whether it's straight or it's squiggly, the amount of work done is exactly the same, which means that the force is conservative and we can associate a potential energy with our electric force or the force due to the electric field. Okay, so let's apply our definition of work as it relates to potential energy. So the work done as our charge moves from point A to point B is equal to minus the change in potential energy, which is minus the final potential energy, subtract the initial potential energy, so that the work done as we move from A to B is negative Q times E times delta Y. Okay, let's make some notes here because this is starting to be a little bit new. So Q is the charge. And I would like you to notice here that I didn't say the magnitude of the charge, I said the charge. E is the magnitude of electric field. I'm going to write a little bit shorthand here. I'll say mag of E as a vector. That means it's the magnitude of the electric field. And Y, in our gravitational potential energy, Y was your distance above the ground. In this problem with electric fields, we still need something to correspond to a ground. With electric fields, the negative plate corresponds to ground. So Y is your distance above negative plate. I'm writing pretty tiny, but I hope you can still see it, and you can make your own notes as well, of course. Okay, let's label that in our diagram. So right here, this is Y equals 0, positive Y points this way. Y equals 0, positive Y is this way. So then our potential energy associated with our electric force, U, we can put an E on it to remind ourselves we're talking about electric potential energy, is the charge Q times the magnitude of the electric field times the height above the negative plate. And I think I will just put in brackets here. It's common also to say Q times E times S or Q times E times D. So we don't always just use Y. Sometimes we use S or D. Y in our heads tends to be pretty strictly associated with vertical motion, but your capacitor doesn't have to be vertical. It could be horizontal or just off on an angle. So the important thing to remember is that the distance measurement, whether we call it Y or S or D, it's the distance relative to the negative plate. So if our path is in the same direction as our force or our field, and in this case, the force and the field are in the same direction, if our path is in the same direction as the force, then the work is positive, which means that the potential energy decreases. which means that delta U is negative. If the potential energy decreases, the kinetic energy increases. Delta K is positive, and our charge will speed up. So if you were doing an analogy with gravity, if you release your charge Q here from rest, it will fall to the negative plate and it will speed up as it goes towards the negative plate. Okay, if our path is in the opposite direction from the electric force, and when our test charge is positive, that's the same direction as the electric field. So if the path is in the opposite direction from the force, that's in our second picture here, where the path goes up but the force points down. What we get in this situation is that the work done is negative. So this is the work done by the electric force is negative. If the work done is negative, then the potential energy increases. It's easy to get the words tangled up here. Our potential energy increases, delta U is positive. As the potential energy increases, the kinetic energy decreases. Delta K is negative. And our object slows down. Our charged mass slows down. So that's like if we take our apple and we throw it up in the air, it moves against the force and it slows down until it gets to the top while the potential energy increases. Let's see now, how do our definitions work if we have negative charges in our electric field? So what if a negative charge moves in an electric field? So that means in our picture, our charge here is negative, negative. That's a charge Q. So when you were plugging numbers into a problem, what you would plug in for this Q here would be negative 1 microcoulomb or minus 5 nanocoulombs. So this is a negative charge. So it can still move up or down in a field. So we can still have a negative charge, start at point A and move down to point B, where the negative plate is still our reference point, y equals 0, and positive y goes up. Or on the flip side, it can start at point A and it can move upwards towards point B, where our negative plate is y equals 0, and upwards is positive y. So that can all still work. In the previous slide, I stressed that U equals QEY, where Q was the charge, and I kind of stressed that it wasn't the magnitude of the charge, it was the charge. E was the magnitude of the electric field, and Y is the position relative to the negative plate. All of the equations we had on the previous slide, they're still all true here. So on the previous slide, we wrote that UE is equal to Q times E times Y. And I'd like to get those definitions written down. Q equals the charge. E equals magnitude of field. And Y equals position relative to the negative plate. So let's trace through and see how our discussion on the previous slide applies here. So first off, any negative charge still feels an electric force due to the electric field. Let's write down that electric force. F equals Q times E. Now, what it means that our charge is negative is that our electric force will be opposite our electric field. That's pretty important. And that's because our Q is negative. So in our our left-hand picture, our electric force is going to be up because our charge is negative. And on our left-hand picture, electric force is still up because it's still charge times field. So now this situation is different from the previous slide. Let's look at our left picture first. Our electric field is down, our force is up, and our displacement is down. So what we have in this situation, because the force is up and the displacement is down, the work is negative. So work is negative, and that's because the force is anti-parallel or opposite the displacement. So I'll even just put that in as a header. So force opposite displacement. That means our work is negative, and remember work is equal to minus delta U, which is equal to minus QE delta Y. Why don't we write that down too? Work equals minus delta U equals minus Q times E times delta Y with all of our same definitions we've written down. So if work is minus the change in delta U and work is negative, then delta U must be positive. Okay, so delta U is positive. That means that U increases. Now that might feel funny at first thought, but let's think about what it means. When our charge Q gets to the negative plate, that's where Y equals 0, and our potential energy would be 0. When it's up here in the middle somewhere, it's our negative charge times the magnitude of our field times a positive Y number. So our potential energy up here is a negative number. It might be a negative 100 joules. So going from negative 100 joules to 0 is actually increasing. So if our delta U increases, it means that our kinetic energy decreases, which means that delta K is negative. And if K decreases, it means our charge slows down. And that makes sense. We have a negative charge going towards a negative plate. That negative charge is repelled by the negative plate. Of course, it's going to slow down as it approaches. Okay, let's look at our right-hand picture next. We've got our negative charge moving up in the electric field. So this time our force is parallel to our displacement. Force parallel to the displacement, or you could say it's in the same direction. Okay, so now what we have is that our work is positive because the force and displacement are parallel. If work is positive, delta U is negative, which means U decreases. And that makes sense when you think about it. It might be 100 joules right here, but when it goes up further, it would get to negative 200 joules. So it would be a bigger magnitude, but still negative. So going from minus 100 to minus 200 is technically decreasing. All right, if delta U is negative and U is decreasing, that means K is increasing. And delta K is positive, and that means that our charge speeds up. Now that makes sense. We have a negative charge approaching a positive plate. It's attracted to it. It will speed up as it approaches. Okay, a couple of big conclusions here. What do we need to circle? So a couple of conclusions is that the potential energy is Q times E times Y. The work is minus Q times E times delta Y. And our electric force, F equals Q times E. So I think those are the important things. And one other thing I'll draw your attention to is when we release a charge from rest, it will move towards lower potential energy. And that's kind of a true universal statement. Whenever we release any object from rest, it will move to put itself in a state of lower potential energy.